Okay, y'all. Let me make an announcement. You're gonna need a pair of these for Monday. You'll want to get this type if you wear glasses. You'll fit over your glasses. Otherwise, if you never wear glasses, you probably want to get this kind because they're way more comfortable. So get a pair of these. They're about $5. You can get them at Walmart, you can get them at Home Depot or whatever. They're called safety glasses.
Are you talking about this Monday?
This coming Monday, yes. What? Oh, that's right, that's right. Don't we have, I didn't even upload a lab schedule. I guess we'll do our lab Wednesday, but this still applies. Yeah. So get a pair of these, you guys. Get a pair of these. Also, don't forget to wear long pants. Don't wear tank tops. Don't wear flip-flops. All of that stuff.
Is it only on Mondays?
Usually on Mondays, yeah. So I guess we'll do ours on Wednesday. It's not a huge lab. It's just we're making some simple measurements and doing simple calculations. But do dress appropriately. And it's those three things that I can't let you do lab if you're violating those rules. You gotta have eye protection, you gotta have long pants. You guys, you've gotta have long pants, you gotta have at least some sleeves. So don't wear strappy tank tops or whatever. So don't forget that. I'll put an announcement on D2L to remind you. When I put something on D2L, does it send it to your email? Does it? Mine's doing that. There's a setting that you set to do that. If you'd like yours to do that, I guess find that setting. I'll help you. Email me if you can't figure it out. I didn't have to set mine. But if I put an announcement up there, it's something that before D2L came along, I would have sent you an email. But just watch out for announcements on there. So I'll say something again about lab before next Wednesday. So we've moved on from chapter E, and it turns out this book has everything organized completely the wrong way that anybody would want to teach it. So I'm kind of going to be moving between chapter 1 and chapter 3 and chapter 4 as I do this. But I promise you my way of going through this is starts the most fundamental and builds out. In general, I go atoms in the periodic table, and then I go into and this will take up a good portion of the semester. And I could put calculations up here, but we already did that. So we're going to talk about atoms in the periodic table, and this will be a little brief, and then I'm going to go into ionic compounds. And then the way this book does it, it's just got everything scattered out in the weirdest way. But I'll give you whatever references to whatever I think is important. For now, most of what I'm going to do will be on the board. I will get a PowerPoint with some of this information in it. By the time next time I see you, God, it's going to be a week before I see y'all again. All right? But let me start by saying this. All throughout the universe, everything, the entire universe is made up of atoms. That's not strictly true because there is such thing as atoms are made up of some particles. And if you split those up, really hot environments or environments with very low pressure, the electrons, protons, and neutrons will just float around in a cloud. That's called a plasma. There's another weird thing called the Bose-Einstein condensate. But other than that, everything else in the universe is made up of atoms. More specifically, it's made up of compounds. But I'll say this. Here are the four compounds that exist throughout the universe. And compounds are just lots of atoms connected together. Or sometimes just a couple of atoms connected. So that's most of what matter is made up of. So there are metallic compounds, ionic compounds, valent compounds, I like to write this list because it's complete all throughout the universe except for those exceptions. It's pretty much all this: metallic compounds, ionic compounds, covalent compounds, coordinate covalent. And this we won't study, and this is really kind of a phenomenon that occurs in aqueous solutions. We don't talk much about this. I think we really just kind of allude to it. But metal compounds, metals are what you knew of as a metal before you came to a chemistry class. Things like this. Things, they're very hard, they go clang. In general, that's what metallic compounds are. We don't do much with those. Ionic compounds, you can think in terms of mineral, ore maybe. Ionic compounds are basically, if you're standing out in the middle of nature, if you want an ionic compound, you pretty much have to dig down and get to some rock and some ore or something. Covalent compounds makes up everything else. In here, pretty much everything is covalent compounds. These are what we call molecules, and we'll get to those in a little while. But you're made of these primarily. You have a few ions in your body. Virtually all synthetic things that humankind makes is made of covalent compounds. So we will focus on these two things strictly, and I will get to ionic compounds today. So there's really an overview, or really there's really an overview of where we're going in the next couple months. Just if you want a map in your head. But we'll start with atoms. Those of you who have taken chemistry before, this should all seem very familiar. Atoms are made up of protons, neutrons, and electrons. Protons. And I'll just use P, E, and N to refer to these. Protons have a positive charge, electrons have a negative charge, neutrons are neutral. And if you've never heard this before, this is the electrostatic force. A positive particle and a positive particle will repel each other. A negative particle and a negative particle will repel each other. But a negative and a positive will be attracted to each other. So this is the electrostatic force. And that's fundamental to a lot of what we talk about in chemistry. And an atom is structured such that neutrons and protons exist in a little nucleus, and the electrons float around outside of it. There's a specific structure that we'll get to that the electrons do, but protons are always in the nucleus, neutrons are always in the nucleus, and electrons are always out here. So all of the atoms that exist in the universe, there are some that have one proton, like this, and some that have protons. And we'll ignore the neutrons, sort of, but we'll talk about isotopes. Those of you who took chemistry before, you remember the word isotope? So I'll talk about that a little. But the vast majority of chemistry, you kind of ignore the neutrons. You don't have to think about them. You don't even really have to think about isotopes. There is some specialized type of chemistry that's done that involves isotopes, but it's kind of a niche. So in truth, we kind of ignore neutrons, but I will talk about them a little bit coming up soon. So we're primarily concerned with protons and electrons. That's an introduction to the atom. The atom that exists that has one proton in its nucleus will have one electron out here. The atom that has two protons in its nucleus will have two electrons out here. And the idea is if you have one proton, it's going to attract one electron. And truthfully, if you have this atom, the electrons going around it, if you zoomed in real close, you would see a negative charge, or you'd see a traveling negative charge, or really we say a cloud of negative charge because it's going so fast. And you would see a nucleus that has a charge, positive one. But if you zoomed way out, just at some distance, to any other charged particles, it might as well be neutral. They sort of neutralize each other. So the charges still exist, but once they get packed together like that, you only have to zoom back a little bit, and then another ion coming by won't be attracted to it or repelled by it. Negative ion can come by, it won't be attracted or repelled. It has to get close to have those effects. Really close. So there's atoms with 1 proton, atoms with 2, atoms with 3, etc., all the way up to about 100. I think just before you get to 100, the natural atoms end, and up to, I think, about 110. We never deal in these, I don't deal with these. They're exotic because they only exist because somebody made them in a lab. And it takes an enormous amount of energy to make them. They're not useful for anything as far as anybody can tell. And they're not very stable, they don't last very long. But if you try to push past there and put more electrons and protons together, it just falls apart naturally. So the universe even limits the number of atoms that there ever will be to about 100. Truthfully, the vast majority of atoms we work with are the smallest ones that have 1 proton, ones that have 2, ones that have 3, and then a few of the slightly larger ones. And those are kind of what make up the natural world. Most of what's on that periodic table are rare, hard to find. You've heard of rare earths. That's pretty rare, but some of those are so rare that they're extremely rarely seen in nature. But they're known to exist. So that's your introduction to the atom. We'll talk a little bit more about the structure of atoms. What else I would say? But this structure, the electron state. All right, I'll say one more thing. The atom is defined by how many protons are in it. The atom that has 1 proton in it is called hydrogen. The one that has 2 is called helium. And these are on the periodic table. 3 is lithium. And let me put it this way, the number of protons in the atom never changes. The electrons do sometimes, but the protons are kind of written in stone. It isn't that you can't play games with, you can split apart a nucleus, and you can make nucleus. But if you split it apart, that's called nuclear fusion, nuclear fission. And if you're making one, it's called nuclear fusion. You might have heard of those things, but this is really something that physicists deal with. We're talking about nuclear energy. It's not really something chemists deal with. So in our class, and in most chemistry classes, we really don't talk about nucleus much anyway. It's all about the electrons. But just realize, if it has 1 proton in it, it will always have 1 proton in it as far as we're concerned. And it has a specific name, it's called hydrogen. So 1 proton, 1 electron, that's the neutral atom. But atoms can gain and lose electrons, which then makes them charged. Meaning if I had 2 electrons in the nucleus, it's not a good example. Let me say I had this. Okay. All right. Electrons. There's 2 of those. Then we have 2 negative charges and 3 positive charges. The first negative charge neutralizes the first positive charge. The next negative charge neutralizes the next positive charge, and then you have a leftover positive charge that's not being neutralized. So this would be a +1 charged atom. Maybe if you looked close, you could see it visual, but from far back, it would be as if it's a +1 particle. See what I'm saying? So for us, chemists, and you guys as chemistry students, it's all about the electrons, gaining and losing electrons. Protons always stay there. Neutrons, they don't really change, but you can find atoms that have, let me say, you've got protons, electrons, and neutrons. I'll just make this up. Let's say this is 17 protons, and a neutral atom with 17 electrons. And let's say it's got, I don't know exactly, but let's say it's got 12 neutrons. And then you can also have another electrons, neutrons equals 14 or something. But they exist naturally, and whenever we get whatever atom 17 is, which would be, there's 17, that would be chlorine. There is some chlorine that's like this, and some chlorine that's like this. Those are what we call isotopes. It's when there's these numbers, the number of protons are the same, but there's different numbers of neutrons, then that's different isotopes of this atom, the number 17. But I'll get to talking about isotopes maybe next Wednesday. Okay, so let's talk about the periodic table. I'll get to talking about why it's shaped like this, because it's shaped like this for a reason. But let me give you the generalities, and then I'll go into ionic compounds. Let's see. You should see this in the top left corner. So I'm just going to do hydrogen to orient you to what's there. This is the name. This is the symbol that we use a lot. And this sometimes called the molar mass. You sometimes see weight instead of mass. I think molar mass is always said that way. I don't think anyone ever says molar weight, but so just a little nomenclature. We'll use this later in the semester. This is called electronegativity. This is what I'll give you for tests. Realize you don't have to memorize the names and the symbols, or the electronegativities, or the atomic mass, molecular weight. So that's why I like this periodic table. So I've uploaded this on Georgia View D2L. So you can download a copy if you want. If you lose that one, you can always download another one. Reference this while I talk. Okay. Oh, yeah. I skipped something. I knew something saying wrong. All periodic tables have the name, or not all periodic tables have the name. That's why I like, another reason I like this one. But this number is important. We call it the atomic number. But it is literally the number of protons. The atom is literally defined by the number of protons in it. The one that has one is called hydrogen, the one that has two is called helium. All right, the atomic number is the number of protons in it. And for any neutral atom, that's also how many electrons it has in it. So if I ask you, I have an atom here that has 26 protons in it. Tell me how many electrons are in it. As long as I've said it's a neutral atom, you know for a fact it's 26. So you can get a little more information than what's here based on what I've already told you. Exactly how many neutrons are there, or vary a little bit. I'm not going to ask you to memorize them. But like I said, I'll bring them up briefly for one topic, and then we'll kind of stop talking about neutrons or isotopes. This all seem familiar to those of you who took this? Okay, to the periodic table itself. Columns are called groups. called it's sort of like if you had a calendar, you had 1, 2, 3, 4, 5, 6, 7, and you come back here, you're 1, 2, 3, 4, 5, 6, 7. It's Monday, Tuesday, Wednesday, Thursday. You could go, that's a period, the period of a week. Just that's why they call it a period, because it's similar to the calendar. It is organized for a reason. But the columns, they all have similar properties. And it's helpful for what I'm going to explain to you. Because if I tell you something about anything, well, for today, the things I tell you, something from the top row, that means everything down here is the same as oxygen, everything down here is the same as nitrogen. I'll tell you what I mean in a few minutes. So that's a little nomenclature. Here's a little nomenclature that all textbooks like to tell you. Those are called, row 1 is called the alkali metals. Row 2, and the rows are numbered at the top. And most textbooks like to mention row 16. I don't know if your book mentions this. I don't tend to ask this on a test, but if you're reading, it might help when they mention these. What did I say? 16. One with oxygen. Row 17. Textbooks love to use that word, and they always mention this one. All the way on the right, the noble gases. So I'll give those to you. That's just really such simple information. I don't tend to ask it on a test. So there's just a little bit of nomenclature. All right.
Wait, aren't the rows left to right?
Yes. Columns. I do that a lot. Yes, it's the columns, not the rows. Thank you. What should I tell you? You see that stair step that goes down like this?
Yeah.
That's an important thing. This top right corner, those are the non-metals. So we're kind of getting to, those are the non-metals. Let's do this. Put up here, everything else are metals. Though truthfully, there's such thing as metalloids. And I don't talk much about these, but let me show you a table. From your book. So can y'all see that? So the green they're showing here, up in the top right, those are the non-metals. So this is important for what we're about to do with ions. And everything that's kind of yellowish, looks yellow to me, are metals. Notice that hydrogen is actually a non-metal. It's just, if you follow the rules that make the periodic table, hydrogen has to be over there because it ends up having similar properties as those over there. The periodic table would also be a little more symmetrical if we moved helium from the top right over to and squeezed it in that notch on the top left. Then at least you'd have two complete rows to start, columns to start with. But helium is over there on the right because it has similar properties to everything down there. We will talk about why that is, but for now, I can keep it simple to start talking about ions. What else should I tell you? So these are non-metals, and hydrogen goes with these. All the yellow is metals. The purple are the metalloids, and you can kind of remember that by looking at that stair step and just remember the exceptions. On either side of these horizontal lines is a metalloid, except polonium and aluminum. We won't talk much about polonium. Aluminum is central to what we'll talk about, but it's not a metalloid. It literally goes with the metals, so is polonium. Metalloids are metalloids because sometimes they act like metals and sometimes they act like non-metals. I don't talk much about those for an introductory class, but okay. So that metals and non-metals, metalloids. So let me do this again. Metallic. That's not how it is. Ionic. Metallic compounds have only metal. So these things, anything that goes plain like this is made up of only those yellow ones. Covalent is made up of only non-metals. Ionic, can you guess what ionic is? It's both. So if you're looking at a compound, I'll show you what a formula is later. Those of you who took chemistry know, but you could look at a formula and go, are these all non-metals? And if they are, then you know you're looking at a covalent compound. If you're looking at a formula that has some metals and some non-metals, it's ionic, and if it's all metals, it's metallic. Like I said, we don't talk much about this. And they are this because the bonding that takes place to bring metals and metals together is metallic bonding. The bonding that brings together a metal and a non-metal is ionic bonding. And the bonding type that brings covalent together is covalent bonding. That's where that name comes from. We're going to talk about ions and ion compounds. Ionic bonding is kind of simple. It's basically, I mentioned before, gaining and losing electrons. Some atoms can be positive, some can be negative, and then that's it. They're going to be attracted to each other, and that's what makes a bond. They stick together with an ionic bond. So let me get to that. Back to the periodic table. Here's how you decide what the charge is. So any of these can be neutral. When nonmetals are in this state, they're neutral. They're not in their ionic form. Same number of protons and electrons. Metallic, same way. It's for the ionic bonding that become ions. So these are all neutral atoms. Like if you've got nitrogen, that means you have 7 protons and 7 electrons. But nitrogen can lose electrons or gain electrons, and it'll therefore have a charge on it. The way you tell what the charge is, so this is important, this is for predicting things. Look on the right side of the stair step, and then go one more out to get away from the metalloids. If you're looking at carbon and you're trying to say, what is the charge on carbon when it's an ion? It can't exist neutral, but when it's an ion, what you do is you put your finger on carbon, but you don't count carbon, but you start counting to the right. Carbon will be 1, 2, 3, 4. It'll be a -4 charge. Because they gain electrons, and say it again. Can't gain electrons. Do you know what you call a negative ion? It's called an anion. And positive ions are called just a little more vocabulary. All of the nonmetals. Oh, thank you. I brought in the second camera this morning. And I thought I had it solved. You can click up here in this corner and switch cameras. But once you start recording, the other one disappears. So I had one on the board and one over there with that screen in. It didn't solve the problem, unfortunately. Where was I? Anions, cations. Yes, predicting charge. So again, let's say sulfur, that's S. If I said, what is the charge on a sulfur ion? You would put your finger on sulfur and you would go 1, 2. So it's charge -2. Truthfully, once you know that carbon is 1, 2, 3, 4, that means, well, carbon is really by itself. This is a metalloid. Nitrogen, 1, 2, 3. Nitrogen is -3, and so is phosphorus below it. Oxygen is 1, 2, -2, and then everything below it is also -2 when it's an ion. Fluorine, chlorine, bromine, what will those be? -1. You can't, so you don't count fluorine, but you count next to it, and there's just one, so it's -1. These are the noble gases. They don't ionize. They don't do anything. They don't gain electrons or lose electrons. Okay, look at the metals all the way over on the left. Magnesium is Mg, and if you wanted to know the charge when Mg is an ion, this time when you're on this side, you do count the one you put your finger on. So if I'm doing magnesium, I count magnesium and I go 1, 2. So magnesium and everything in its column, including beryllium above it, this whole column becomes +2 ions. So that's how you can get the charge quickly from the periodic table. We'll talk about the structure of atoms, which will make it obvious why this is true. And of course, this first column, these will all be +1. So the summary of that is this whole column is +1, this whole column is +2. Carbon is -4, these are -3, -2, -1. There's only one that kind of stands out as weird, and it's aluminum. If you count aluminum, you go to the left. All this is blank, so aluminum is 1, 2, 3. So aluminum is +3. So you can get that from the periodic table if you remember what I just explained. When we write these, so here's the symbol for magnesium, and I'll write magnesium 2+ over here. But here's neutral magnesium. That means it has one row up, so it's 12. So if I ask you how many protons it has, you look at the periodic table, you look at that integer that is the atomic number, and it tells you that it's 12. Therefore, for this, you know the number of electrons is 12. But for the +2, it's lost 2 of the negative charges. You have 10. Does that make sense? You could do this for the nonmetals too. Chlorine. Chlorine, what's the charge on chlorine? I already gave it away. -1. This is weird. I don't know why. There's a couple places in chemistry where we don't put the 1 down. We write 2, 3, 4, 5, or whatever for this. But when it's just 1, we just put the negative there. Same with positive. Sodium, Na. We just do that instead of putting one there. Don't know why, that's just a convention in chemistry. Chlorine, how many protons does chlorine have? 7? 17, right. How many electrons does this have? Also 17. How many here?
16.
8. Gained an electron. The reason this is negative, it just has an extra electron. It has one more electron that it has protons. The reason this is positive is it's lost its negative charge, a couple of negative charges. So those two positives are coming from 2 protons in the nucleus that aren't being canceled by the electrons that were there. Those 2 electrons have left. You guys good so far? Ions. So let me go through a formula. Ionic formula. The way you do these formulas is, let's say I want to make, I want to take the ions of a nonmetal and a metal and stick them together. What happens is, they have to be neutral when they come together, so let's do magnesium. So if I want to make something out of magnesium and chlorine, we put these together in the lowest ratio we can, kind of like a reduced fraction all the way. Reduce a fraction as far as you can while keeping the whole numbers. If I have a magnesium ion, it's 2+, and I want to put chlorines on there enough to make it a neutral particle. How many chlorines do I need? Yeah, well, one more if you're counting this one. But we need a Cl and another Cl. These are headers. That's what we're going to make into our formula. And the way we do the formula, we go Mg, there's one of those, Cl, there's 2 of them. That's the formula, except this is another case where we drop the 1 off. If it's just one of these, we don't do that. So MgCl2 is the formula unit, the chemical formula, the ionic formula for this. It's called magnesium chloride, but I'll get to the naming in a bit. Let's do another one. Let's do oxygen. Oh, I should mention that the positive one always goes on the left, and the negative one always goes on the right. So I'll write oxygen here, and all right, beryllium is near the top left, Be. Oxygen is near the top right. I want to make an ionic compound out of this. What would the formula be? Here's the process. What is the charge on beryllium? What's the charge on oxygen? It's 2 negative. Oh, I don't know why the chemists put the sign on the right side of the number. Don't know why. They've done that forever. So what would be the formula for this? If I wrote down the Be and decided how many oxygen atoms I need, I only need 1. That's the chemical formula. You might think it should have 1, but like I said, we always drop off the ones in chemistry for this case. Simple, right? All right, let's do. Let's do calcium and nitrogen. Calcium is in the third row down on the left. Third row, third row. Nitrogen's over there on the right near the top. So what's the charge on calcium? Two plus, or plus 2. How about nitrogen? Okay. If I'm going to make a formula, when I bring these together, this is a little tricky. This is the only case for these simple, predictable ones that you have to do this. It's sort of like the least common multiple. If I have 3 calciums, I'll have a total of plus 6. And if I do 2 nitrogens, I'll have a total of negative 6. If I have that will equal plus 6, and that will equal negative 6. So the formula, you have to have 3 calciums and 2 nitrogens.
Isn't the 3 supposed to be out front?
Out here, you are remembering something from a chemistry class, right? But that comes up when we do the actual reactions. I'll get to that. This is just that basic formula. This would have been in the reaction, but sometimes you have to have 2 of these for the reaction. Sometimes you have to have 6 or something. We'll get to reactions later. You see how to do the formulas? Quick, explain it again. It's all about balancing the charges. So if you start by going, okay, calcium is plus 2, nitrogen is 3 negative. It's not 1 to 1, and then you have to go, how am I going to put these together to make it neutral? Same number of negative charges that there are positive charges. If I tried to go just 1 calcium and 1 nitrogen, that doesn't do it. Because that's plus 2 and that's negative 3. So this would end up being negative. If I tried to put 2 nitrogens on it, well that's even worse. I've got charge 2 here and a charge negative 6 here. But if I tried to do that, now I've got a charge 6 here and a charge of negative 3 here. So you have to play around with it until you get them. But this is the only case. The 2 and the 3 or the 3 and the 2. This is the only weird case like this for the really predictable ones. Did you follow that? It's all about balancing them. And it's kind of like the least common multiple of these, which would be 6. So you're trying to match it to a 6. Did I answer your question?
Thank you.
You can also have, give me a 3 plus ion. There's actually only one that I mentioned. Give me a 3 plus ion. Huh? Aluminum. It's the only 3 plus ion I've mentioned so far. Let's use aluminum. And give me a 2 plus, it's not a 2 negative.
Sulfur.
All right. Same deal here, except we're going to have 2 aluminums and 3 sulfurs. 2 aluminums, that gives us a plus 6, and then sulfur, 3 of those, that gives us a negative 6. You see? So you can be in a situation where it's 2 and 3, or you can be in a situation where it's 3 and 2. And that's the only part that this gets tricky with. You follow this? I love these water machines. Do y'all use these?
Yeah.
Huh?
Like Yeah.
Heck yeah. I wish it was colder. That's my only complaint.
It's not as warm as the one in my dorm, so.
Oh, really? The one upstairs is warmer than this one. UNG, they were all cold. It was so good. They had the exact same setup, but it was almost ice cold. All right. That's all the simplest part of ions and ionic compounds. I guess I should do naming. So you have your ions, they come together, they make a compound, aka an ionic compound. Okay, let me list a few. I'll do that one. Let's do, let me get a few ionic compounds down. Oh, that's a crappy one.
She said she would. She was like, I just got a new one. She said,
Okay, well, let's just go with those. Here's the name for this. These have names. This is called aluminum sulfide. The way you name these, you always name the positive one first. The first part of the name is literally that name that's on the periodic table. You just name the positive ion. The negative ions, this is sulfide, not sulfur. This is bromide, not bromine. And this is nitride. And that's it. A little bit of the naming we do for the covalent compounds will involve words like di, tri, tetra, penta. Just keep in your head that when you're naming ionic compounds, we never use those. This is a common mistake students make. So this is not dialuminum trisulfide. This is not tricalcium dinitride. It's just calcium nitride. And that's because chemists know the only charge calcium will ever have is +2, and the only charge nitrogen will have is -3. So we know what it's going to be called.
With the ending on the Anna, how do you what's the last, like, what are the different situations?
The rule for putting the IDE on there, I think it's easier to just write them down. That's what I'll do. They are in your book. I'll tell you which table they're in. Remind me to bring the camera back. They are here. It's all the way up to 4 molecules in compound. See, looking through this book, it's just crazy to me. So they are in table 4.2.
excuse me. Can you put it up on this screen, please?
If the screen goes out, y'all let me know. How long has it been like that? It's a bad connection. We have a few issues in here. If I don't bring the camera back, tell me to bring it back. If one of the screens goes down, tell me. I've got slight technical issues, but it's something I can solve. Not exactly sure what the rule is. There's probably one general rule. I don't remember what it is.
I think I have it from my dad's notes. I was just wondering.
Is there a general rule?
Yeah, I have like the whole thing.
Is this the book? This Monday?
Okay. So naming is simple. You just have to do the I at the end. And I think if you read through this list, you can just kind of remember them. Bromine becomes bromide. Fluorine becomes fluoride. I think it's the very last vowel. You cut it off there and then put IDE on it. Seems like there's one of them that's weird. This isn't a complete list. That's why this is weird. Is it a complete list? There's telluride and iodide. Iodide is not there. Oh, telluride's a metalloid, so let's not deal with that. Okay.
This isn't the part where it's like hydrochloric acid, like it's not that, that you're just talking about.
No.
Okay, I was thinking of that.
We actually won't get to acids. They do that 12-12 here.
Oh, okay.
So we won't even do acids.
But there's no like other name, it's always IDE.
For these there are. For these ionic compounds there are, yeah.
Okay, thank you.
There are molecules that are like, you could call it carbon tetrahydride or something like that. But we call that methane, so nobody really uses the tetra and stuff. Or in rare cases, they do. Okay, so let me get to what's slightly complicated about ionic compounds. You notice I really haven't alluded to everything on here. You guys, this is important. I haven't alluded to everything that's on here. I pointed to these and I pointed these up in the corner. I guess I've alluded to hydrogen. This square here, I want to bring up. Now, I didn't have the camera up yet. Just tell me to bring it back. But let me bring up something here. Okay. So let me show you this way. This rectangular part here, going from row 3 to row 12, and then all the way down to the bottom, that whole rectangular part, those are called the transition nodes. So when I was giving you the names of columns, I should have told you that that fat part in the middle is the transition nodes. I said row again. I'm going to column 3 to 12. Those are called the transition nodes. And those are what I want to tell you about next. The thing about those is they don't tend to have only one charge. They can achieve this charge and they can achieve this charge, always positive. But sometimes they can lose 3 electrons, and in another case they can lose 5. Weird stuff like that. So they're not predictable from the periodic table. They're predictable if you memorize them. They might be predictable once we talk about atomic structure. But they're not predictable from looking at the periodic table and counting to the left or the right. So when these show up, they usually show up like this. Instead of writing 2 atoms in here and then asking you the formula that you would get from, I'll kind of work backwards and I'll show you the formula. And then we'll predict what the charge is. This is iron. It's kind of down. It's at the top, right in the middle, top of column 8. And the Fe. Both of these compounds exist. And the difference is the Fe has a different charge in each one of them. Fe2, 3, Fe2. And they actually have different names too. So I could ask you a question like this. I could give you this and say, what is the charge on iron? Fe is iron. Well, you can find the charge on iron because you know the charge on oxygen. It's definitely going to be -2. It doesn't take any other charge. And the way I tell you to do this is just make 3 oxygen atoms, because there's a 3 there, and go 2 minus, 2 minus, 2 minus, those add up to -6. I'll put the minus on this side because I'm going to make a little math thing out of it. There's 2 irons, so I'm going to go Fe, Fe, but I don't know the charge yet. This has to equal 0, meaning I have to have a +6 here. I guess I'm saying if you add them together, you don't really have to do the math, they just have to match. So if you find out that you have a -6 charge in this formula unit, that tells you that you have to have a +6 charge on the positive side. And you've got 2 irons, so you're going to split that charge among the 2 irons. So the 2 irons are +3 plus. And that's how you figure out what the charge is on iron. I'm not going to have you memorize the possible charges for iron, but you can always find the charge on any transition metal. If I show you a legit formula unit, you can infer it by looking at the non-metal, whose charge you absolutely know, and just go through this process, and then you divide it among however many. What do you think the charge is here? 2 of, sorry, that should be FeO. My bad. I'm messing up your notes, I know. I mess up on the board, I'm gonna mess up your notes. That should be just FeO. So what do you think the charge is on iron there? If there's only one of these and it's 2 negative, then the Fe has to be 2 positive. And that just goes to show you, illustrates that the transition metals can have more than one charge. So that's where those get tricky. When it comes to naming, you want to do another one of those? Yeah. Let's use, I like the vanadium. I'm sure that looks weird, but vanadium is in the top left of the transition metals. Row 5. You can also have those 2 are both possible. So the charge here, this is actually just like the iron one I just did, so maybe I should have done this. But the 3 plus 2 charges, these are just like the iron one. I really chose 2? No. No, that one's different. Okay.
Is oxygen -2?
Yes. -6, that means you gotta have +6 over here. When you look up here, you go, 2 of these, how do I split that +6 into here? 3 plus, 3 plus. So here, vanadium is 3 plus. And over here, you've got 2 oxygens. That way, 4 minus, that means you gotta have a +4 here. You've only got 1 V, so it's 4 plus. And vanadium can even do 2 plus and a handful of others. I'll do one more of those. All right, what do you think here? There's only one oxygen. This is copper, Cu is copper. So what's the charge on copper here if there's two of them? Yes. You've only got one oxygen and it's two negatives, so you've got two negatives. You need two positive, and you've got two coppers. Splitting that among those two coppers is one plus. So there's such thing as copper with plus one charge. Ah, thank you. So Cu2O and CuO, you only have one oxygen, so it's got to be two negative. You split these two into these two, each one gets one. This one you can probably see directly, because there's only one of each. What's the charge on copper there?
2 plus
This is. You want to do more of those? I will come up with questions for all of this, just like I did the math problems and put them on D2L. I just haven't prepared them yet. I've given up on ChatGPT. It takes me more time to do stuff, and I never really quite get finished because it just keeps putting mistakes in. Our metric to metric conversions, were those correct? I copied those over to a different type of class that I'm teaching, and we discovered that they were all backwards. Ours were correct. We went through them in class. I must have given them the one that came straight from ChatGPT. So I messed them up. For like a week, they were confused. Probably leave early today. All right, do you want to do more of these? Okay, I will make questions like this online for you to do. Okay, here's the next thing. For some reason, I like iron. I like this example. All right, these are the ones we've done. And in this case, and this one's B, this one's 6. And this is. All right, here's how the naming works. It's just like before where you go straight off the periodic table. I used oxygen in every example. I don't think I meant to do that. And then oxide, just like before. But let's say you're a lab tech, and I ask you to go get iron oxide out of the stockroom. You get halfway there, and you go, oh wait a minute, which one does he want? Does he want this, or does he want this? That alone doesn't differentiate these by name. You see that? They're called exactly the same thing. They need to have unique names. So what we do is we put this charge in parentheses in the middle. But we do it in Roman numerals. So this is iron 2 oxide. This is iron 3 oxide. This is vanadium 3 oxide. And this is copper 1 oxide. I see some books that do it like that, and some of them put what's called, I think, called the title. That's the naming twist when it comes to, if it's a transition metal, you have to have that parentheses, and you put the charge that's on the positive ion in the parentheses. So now when I send you to the stock room, I need to say either iron 2 oxide or iron 3 oxide. I need to tell you what I mean so you can read the label and get the right one off yourself. You see what I'm saying? That's what makes them unique, the parentheses.